for a velocity time graph, position versus time. So we're going to do just a really quick little graph here. And we'll put in time, and we'll do that in seconds. And we're going to make this v, or velocity, and we're going to make that in, what's a typical velocity unit?
Miles.
Meters per second in science, we'll do that. So we'll have that. I do want to make a straight line along that graph. So we'll start with this. Okay, there we go. So we have a straight line on a velocity time graph. Now that's going to be a little different than straight line. Okay. I'm going to put in some numbers because it's really, really hard to teach this without some numbers. So we'll put in 5, 10, 15, 20, 35. And for the sake of argument, we'll say that this is ending at 35. And then we'll put in some times. 1, 2, 3, 4. And I could talk theoretically, but it is much easier to do this. Now, this is actually velocities. It's comparing velocities versus time. It's not comparing position versus time. You have to remember, this is a completely different graph. So a straight line on a velocity time graph will mean something different. So let's just analyze this for a minute. At time 0,
Going 10.
okay, the velocity equals 10 meters per second. What does that mean? It means what?
The car's already moving when you're starting it.
When you started the time. So already moving. And each second it's going 10 meters. So already moving. It's going changing as time increases. Yes. It's actually getting faster and faster. Not uniform motion. For uniform motion, it will be going the same. Changing. It is changing velocity.
Isn't that like a car going?
Possibly.
10 miles an hour.
And what's happening is as the time is progressing, it's getting faster and faster and faster. So at the end, at 9 seconds, how fast is it going?
35.
It's going 35 seconds. The velocity is 35 meters per second. And we could convert that into the velocity. Is that the velocity is changing at a constant rate. Listen to the wording of that. Velocity is changing at a constant rate. But the object is not moving at a constant velocity. Okay, so move that up a little. Change that. But that's an important thing because sometimes people with the English get those ideas mixed around. The velocity is changing at a constant rate. That's what we mean by a straight line. But the object is not actually moving at a constant velocity. So each second it's not going the same distance. If we were doing a motion diagram on this, if we were doing a motion diagram, you would be having the velocity vectors would be increasing. So just real quick, a motion diagram. Just like we were doing before, you would have a velocity vector that was at 10, and then it would be getting faster and faster and faster like this. So that would be our velocity vectors, getting faster. So my question is, if it's getting faster and faster, what would be true about the word acceleration? Positive acceleration. It's also constant acceleration. So let's get rid of some of these things, and I'll be able to say that this particular diagram, we have constant positive acceleration. So we have constant positive acceleration. Now, constant positive acceleration. Does anybody see a connection to the graph and this term right here? What other word would represent this constant? Pardon me? What were you saying? You said straight? Change in over change. Good. Change in velocity over change in time. So guess what? We have delta V over delta T. Change in velocity over change in time. That suspiciously looks like an S word, which is slope. So the slope, this, just like the slope on a DT graph gave you, is going to give you acceleration or average acceleration.
Say that one more time.
Just like the slope in a DT graph gave you velocity, the slope on a VT graph is going to give you acceleration. So it's a change in velocity compared to a change in time. It's V1 minus V0 over T1 minus T0. This is equals, this is equals, this is equals. This is A bar, which means average acceleration. And we're going to have to get you to wrap your mind around it. This. Does anything in this graph tell you where the object is located? No. It just tells you how fast it's going at various different times. It does not tell you where it is, just how fast. So we have to keep that in mind. It's very different than a DT graph. We're going to work our way through that and get some other equations for those things. But just so that we can, I want to add a little something to this graph. Okay, so we're going to add a little something to this graph. So I'm going to take this away. Wait a minute. Not just yet. There we go. Now I'll take that away. And what I'm going to add in is this graph right here. Okay, so the slope is 0. So we want to keep that in mind. So the slope is 0 on this one. And if the slope is 0, no change in what?
Velocity.
Good. No change in velocity. But what about the position? The position, good. Say that. Which means, okay, so let's get that written down because that's an important difference in a VT graph that people sometimes miss. Okay, we said that the velocity is constant, and that means the object is moving, okay, at a constant rate, not that it is at rest. Only time that the object is at rest is when? Um, That's when they're moving at the same speed, but it's not necessarily when they're at the same location. It just means they're moving at the same speed. So you can have two cars that are moving at the same speed, and then, okay, although they are related. And we'll put together like a chart as far as how they're all related.
What if they're average?
If its average is 20?
Yeah. So what they kind of like right here.
Well, average velocity um, would, PT graph. All right, so we're going to move on. I want to show you another thing that happens with graphs. All right, and I'll probably show you this more than one day because this gets a little bit tricky. All right, we're going to have a graph. Now this time, we're going to get into the negative zone.
Doughty, you should just like make a graph sloppy.
But I want to do different things with these graphs.
Like make a generic graph and just copy it.
But I want to do something different with this graph than the last one. It's different. So this one we're going to have still time here. It's still going to be a VT graph. Let me fix it. All right. So it's still a VT graph. All right. Now this one we have to talk through, and you have to really, really, really think this one through. All right. I want to take a look at this, and we want to talk through what's going on with this graph. It actually is not moving backwards the whole graph.
No, the first part is slowing down.
Beautiful. Okay. Now, here we have a positive velocity. Okay, so does it start at rest?
No.
No, it starts in motion.
That looks like it's like 35.
Well, we don't have numbers. It starts in motion.
About 5.
In what direction?
Forward.
In a positive direction. Okay, I want to do this one thing at a time because some people are not seeing it yet. For now, yes. Okay, because we can have, well, I'm going to do it a little bit at a time. So for now, yes. We know it's not starting at rest because here the velocity is in the positive direction, whichever the positive direction may be. The positive direction may be up. As a matter of fact, this graph is actually showing that. As the time is going on, it's getting slower and slower and slower. So through here,
For some reason, I thought you were talking about a rock.
the object is getting slower. It's slowing down. Okay, so think about a ball that you've thrown into. Higher and higher, and I know that's okay. So we can't say at rest, but we can say at this time, velocity equals 0. Vertically, yes, but when we do those problems, we're going to have to think of vertical and horizontal separately and then put them together.
But if you're going horizontal, you don't have that zero.
Well, actually, because you can't have horizontal without something going on with vertical unless you have some kind of propellant on that thing. But if it's just a projectile, there is always a horizontal and vertical part. I wanted, This right now, this is difficult for many people to get their mind around, so I'd rather not combine the two right now. Okay? Because right now there are some people that are just struggling with. Mhm. Yes. Yes. So through here, it is getting faster in a negative direction. Getting faster in the negative direction. And the reason for that working is gravity, okay, on Earth and on the moon. And really the reason that we can actually use this in real life problems is because what's going on in this particular scenario. The object is starting in a positive direction. It's slowing down at one particular instant. It's 0, but then it starts getting faster going backwards or in the negative direction. Okay? The whole time, the acceleration is the slope. George has the can have. This is actually a negative velocity equals 0. And I want you to write that down because I want you to read it and see it and think about it. Okay? This graph has a constant negative acceleration. Okay? The acceleration is not 0, even when the velocity is 0. Okay, so very, very, very important. Zero. Very, very important. Even here, the acceleration is not 0. So if you are organizing your information, like when we get to do problems a little bit later, you're organizing your information. The acceleration, on Monday, I'm going to start relating this to integrals in calculus. So I just need to turn off this recorder real quick.